This is a walkthrough of how you can use InfoWorks ICM as a central database to manage your EPA SWM models. And this is a feature that's newer because ever since we added support of the SWM engine inside of ICM, which came out in version 10.5 or late 2019. So now you can import SWM models and you can use the whole SWM data schema, the SWM engine, get the same SWM results. In a SWM network, and at the same time, you can also have a parallel network that uses the ICM data framework and data engine. So here, this node is asking for ICM fields like chamber roof, chamber floor, whereas this node in the SWM network is asking for SWM fields like max depth, and so on. So I'm going to walk through how you can manage this SWM model in terms of updating it, managing scenarios, managing the data updates from GIS, as well as pushing out models to EPA SWM and pulling in those models with reviewing the data for updates. So really, it could solve being a central data repository for your library of different SWM models. So for those new to the InfoWorks ICM environment, we can manage a number of different models in the database. In this case, I just have this one model, but you can open up different models. You can drag on different themes. So here we're looking at a simple model. This model happens to have subcatchments, so it's a combined sewer system on this main area. And then this branch over here is just using RDII nodes because it's a separate sewer system. So we're using RTK to simulate the INI. So we can drag on different themes, such as this RDII catchment area that highlights the contributing catchment area based on blue. If it's green, then there is none, which is this portion of the network with subcatchments. We can also do themes based where we can view the pipe diameter. We could highlight where the dry weather flow contributions are coming from, especially. So areas where there's higher population. And so on. And you can also do themes based on actual custom expressions. So this one is actually doing a theme based on a field that isn't in the database, but it's calculated as it applies it to the map by taking the upstream invert minus the downstream invert divided by the length to give us a slope theme. And so really within the mapping of ICM, there's a lot of customizability you can do if that were a word. So here on my conduits, in this case, you can stack up really a theme on any of the data, any of the results that you want to use. But you can also even do it based on SQL queries, so such as this one, which is using an equation so as it runs. So here we can see cases where we have really low slope pipes, which can be problems in sewer systems. All right, let's go back to the default and let's review some of the data. So if I double click on a pipe, I can see its data here. And you can see these are typical SWM fields like length, conduit height, which is really the diameter in SWM language. And you can also see some of the flags that have been associated with this. So this tells us where the data came from. So the IDs come from SWM, and if I hover over it, it says from legacy SWM model. I should also mention all of these flags and colors are user customizable. So these are arbitrary flags that I defined for this database. It can be unique to each city. We also have a flag for GIS data. So in this case, the pipe diameter and length and some of the invert elevations are coming from GIS. But you can also track user edits. So in this case, one of the invert elevations was modified, and you can see it has my initials, NG, so it says edited by Nathan, so that another modeler reviewing this model would be able to understand why this elevation does not match GIS. Well, maybe I need to ask Nathan to see why that change occurred. And as you're making changes in the model, it can always track your initials. So like if I enter a number here, as I do it, it applies my initials because I've taught it to do that. And I'm going to click Edit Undo to undo that. And we can also look at the history. So ICM tracks the history of every save and change done in the model. So you can see that this particular pipe was changed 3 different times. One is version 1 of the network. That's probably when the pipe was born, when it was imported from SWM. But then there's a few other changes, and we can take a look at the details of these changes. If I go to previous, this is version 1. So this is when the pipe was born, we could say. And then later on in version 3, it looked like someone added data flags. So version 2 happened in the network, but it seemed like there weren't any changes to this specific pipe, so it's not reporting anything here. And then if we jump up to version 6, that's when a user with the initials NG changed this pipe elevation. We can also click on the full version history, but this filters out the specific changes for that one pipe. And you can also review this over the whole network whenever you want. So you can click on the entire model and you can see a version history. So this model has 7 different versions, all edited by Nathan. You can see the relative number of changes as well as the comments made by the user. And we can also select different versions. So you can see earlier on November 4th, Nathan corrected for flat upstream pipes. So if we wanted to compare the current version to a version before that, if I click differences, we can select the changed objects, do a few other options, and say show differences. This is a report of the changes that have been made, but if we zoom out, we can see all of the different pipes that Nathan happened to change. And that was because of there were some issues with the GIS data that came from the SWM model where there were some flat slope pipes, and so they were resolved with a query. So let's take a look at updating this model. I'm actually going to change scenarios, which I'll talk more about later. But we're going to update the model from GIS, and we're going to look at how we can then manage updates from a data flag and data cleanup point of view. So let's take a look at this little branch of new pipes that were added into this new subdivision. So we can see that these pipes have already been added, and they already actually look okay. But the GIS data actually has some problems here. So I'm going to go ahead and import, and I'm just going to walk through some of those types of issues. So if we go to the Open Data Import Center, this is how we can get especially GIS data into the model. So if I go to pipe, for example, or conduit is actually the term. If I point at some GIS data of Greenville pipes, I can load a field mapping between ICM and that shapefile. So here we're mapping the ID. The ID is required because that's how the importing is done. So we're using asset ID. We're also pulling in the node connections. We have conduit height, conduit width. And I'm going to apply some default values. So it's going to apply upstream invert and downstream invert. And then if those values are missing, you can tell it to use a default value of 0 in this case, because I want to force it to break the model a little bit. And I'm also going to add a default user text that just says updated, so that after this process, I'll be able to easily see which pipes just got updated. I'm going to choose some options like overwrite the existing model. And as I update, I also want to apply flags. So this data is coming from GIS. And so I'm going to use these flags here to say that the data was done by GIS. In fact, I could go ahead and use my initials for the default because I'm manually defining that right here. So I'll go ahead and click import. It updated 6 existing pipes. Let's close that. So you can see that the GIS came in. It now updated my IDs, my conduit diameter, and it was missing the elevation, so it kind of broke that for me. And I could also import the nodes and everything, but another actual approach that you can do, in case you don't really want to manually do all that mapping that I just did, you can actually write a script that will import and update all layers for you all at once. So just as an example, I just put all that into a script and I created like a simple UI prompt, and I can show that script for those interested. But it's a swim network. We're importing. Let's say I want to update pipes and manholes, but I'm going to leave out pumps and subcatchments for now. I want to use overwrite, and let's do my initials NG. So just to be clear, I am re-importing because you'll notice I clicked edit undo because I'm not going to go with that previous import. I'm going to go with this custom script that's going to do it all at once. So the script log says it's done. It finished the data exchange. And now you can see my profile has several problems. And this example is just to show some different ways that data, you can import and update from GIS, but sometimes it's going to come in and there's going to be problems in it. So I want to talk through the process of how you can detect and fix those problems. And namely, my favorite way of doing that is with SQL queries. So another feature in ICM is the inference tool, which is where you can apply built-in logic to correct some of these problems. In this case, I'm gonna custom control it using my own SQL queries. And really, these custom queries, they can be pretty simple. They can be complicated if you want to. And if you want to try something complicated but you haven't yet, you could always ask Innovyze for examples. I have been building up a library on GitHub for anyone interested of different example queries to help you get jump started on using these to help automate and streamline certain modeling tasks. But here I just created my own little prompt window with these lines of code, and it's going to check for several different common elevation problems, and it's going to apply logical assumptions, and it's also going to flag it as I go. So for example, if the invert on a conduit is missing, we're going to grab the node invert if it's available. And if the node invert is missing, we could have it try to grab the minimum upstream invert of downstream links. So it can be a little bit confusing. So that is the query. Let's go ahead and select all of these pipes because you can choose to run it on just a selection. So I'm going to use this flag inferred, and I'm going to assume a maximum node depth of 10 in case I didn't have a ground model. So now that fixed my profile, and you can see I now have these flags of inferred data where I have these elevation issues that have been filled in. Of course, it all looks okay now. The model is going to run, and it's going to be reasonable results. But now I know in the future, when I get the chance, it would be great to maybe even send this selection of pipes to my GIS team and say, hey, we're missing these elevations. Whenever we can get a field inspection, it would be great to get those filled in. So over time, this database can continue to improve because we can start filling in the gaps of where the data needs corrections versus the fields that have already been field verified. We can trust those values. All right, so that is a little bit of updating the model, importing. Let's take a look at scenarios because I did that in a scenario called new subdivision. We also have a few other scenarios. So some large systems, larger cities, will tend to prefer to model their system in smaller chunks. So in ICM, we can have different portions of the network that we can model, and it's pretty easy to create scenarios and trim that down. And then we can also have future build out scenarios of those existing scenarios. And the benefit of doing it all in ICM is that when we do updates on our base scenario based on existing in-field data, it's going to roll those changes out among all my scenarios. So I can do an update from GIS to one master copy of my whole system rather than having 20 different models floating around that we have to update on data servers, and it can just end up being an administrative nightmare. So we have these different scenarios, and you can also actually automate changes to scenarios using SQL queries. So for example, I'm going to expand this, and I'm going to write a query that's going to add scenarios. So in this case, some of the 2030 scenarios have already been added, but I'm going to add some 2040 scenarios based on other existing scenarios. So it's basically going to clone certain scenarios for me. So it's going to do that. And this script does take just, depending on the size of your system, it can take a little bit of time because it is kind of creating a new scenario copy, and then it's re-trimming out those extra objects. If it was simply creating clones of the base, it wouldn't take as much time. But so those scenarios are done. And so like if I expand this, I can see I have existing downtown, I've got 2030 downtown, and I've got 2040 downtown. But right now, all of these scenarios are actually the same. So what we can then do next is we can actually modify the values in each scenario, even using a script. So I could manually select each of these scenarios and make changes, but maybe I want to write a script that's going to make changes to all scenarios for me all at once. So what we're doing in this case is just a very simple, trivial example of multiplying the base flow by 1.1 to add 10% to our dry weather flow in 2030, and we add 20% in 2040. And we do that for each of those 3 different basin future build-out plans. So I'm going to go back to the base, and this is a query that runs on the selection, and I'm going to go ahead and just run on the whole network. And so I'm just going to drag that on, and it's done. So, so now, just to give an example, if I go to existing downtown, what I can do is I have a query where you can also use queries to actually report data. So here we're doing a select and grouping by feature. So if we drag that onto the network, make sure we land it on the network, it's summed up that we have 185.7 gallons per minute of commercial and 191 gallons per minute of residential load in my existing downtown scenario. If I switch to 2030, I can drag this in, and now we have a little bit higher demands, and go over to 2040 downtown and drag that in, and you can see that the demands were scaled appropriately. So, so ICM can manage the version control, the data flags, the integration with GIS, the different scenarios. There's SQL queries that help you review data across different across the system. You can write queries that will trace through things and apply logic. And what I like about it is that the queries are actually pretty powerful because the database was designed by water experts for water experts. So it has an inbuilt understanding that, for example, the foot bone is connected to the leg bone, is connected to the knee bone, is connected to the thigh bone, to the hip bone. So you can actually write queries that can move from object to object because it understands all of that connectivity. So that's helpful for just being able to automate logic with some of these tools. So next, before looking at running a model and results, I want to explore how you could then, maybe you have a large modeling team and some people are still using EPA SWM, or maybe you have to interact with outside contractors and consultants that don't own ICM, and you want to be able to seamlessly integrate back and forth in and out with EPA SWM industry standard and get kind of same results. So, so once I'm done with these changes that I've made, I can click Save, and now I'm going to merge in those changes, and so you can see now I have this new version of my model, etc. But once I now want to push that out to SWM, I just choose Export to SWM 5, and now it acts as sort of a SWM model library. So I can choose any scenario. Like let's say I want to export out my existing Southwest branch, and I can also actually choose any version. So I can choose any version of any scenario, and I can push those out. I'm just going to use my latest version, and we're going to dump this on the desktop in a folder called SWM and give it a gibberish name. And so now that INP file has been sent out. I'm going to open up plain old EPA SWM, and I'm going to open up that model. We got a couple warnings as it opened up the model, because you can see there's a unrecognized keyword, inadvised supplementary data, inadvised supplementary. So there's some extra data that we track when we manage the swim file, but rest assured that the EPA swim is going to be fine without those generally. So now let's say that I am an outside contractor, or another modeler on your team that's doing some swim-based work, and I want to make some changes to this model, because maybe I'm looking at some other design, and we don't have time to do it in ICM because other people are using it. So I'm going to add a node right here, and I'm also going to add a pipe. So I'm just going to, just for fun, do that. Click escape, and let's go ahead and give them some better names. Let's call this new junction. We'll give it an invert elevation of 730, a max depth of 8 feet, and let's give it some inflows. So how about some RDII flow? We'll point at this existing RTK, and we'll say it's 4 acres. So there's that node. Here is a pipe. We can call this new pipe. And let's give it a max depth of 2 feet. And that should be good enough. And let's do a few other random changes. So let's say at this node, we are ramping up the flow that we are getting at this node, so we can boost up the sewer shed area, because maybe there's some upstream flows being added. And along with that, let's upsize a couple of these pipes. So let's change this max diameter to 3 there, and 3 there, and 3 here. And let's just do a couple other random changes. Let's choose a bigger pipe so we can see it more easily. Just arbitrary changes, just for fun. We'll give this a invert. We'll change an inflow a little bit, because that's pretty easy. All right, so let's say I'm done with this model. I'm happy with it. I save it. And now we want to bring these changes back into ICM. We want to merge it with that version controlled, data flagged, managed model. So, so here's my model. It's got data flags and everything. And so now we're going to update those changes from the other system. And one way that we can do that, there's a few different approaches. I'm going to just create a new simple model group, because what I might prefer to do if I were managing this model is, rather than just importing that swim file directly, let's say I want to pull it into ICM where I can compare it side by side. So I import that swim file. We just get a few warnings, errors, and when you import from swim, it's going to import the network. And in ICM, we manage and maintain the network separately from the rainfall time series, the run, the climatology, and so on. But so here is that network as it was in EPA SWM. And so now the task is to merge this data into my actual model. So let me go to existing Southwest branch. This is the particular scenario that we want to merge it into. And in general, when you have different model files in ICM and you want to compare and merge and control them, the best way to do it is actually to use this compare tool. So in this case, I would say my differences from another network, and I would just drag this one in, and I could say existing Southwest branch. We'll select the changed objects. I like to choose these options. And I would click show differences, but unfortunately, because this is a new network, ICM doesn't actually recognize this as being a compatible the same network for comparisons. So in general, if you do happen to have multiple versions that people are splitting off and working within ICM, this is the approach, and you can actually push the changes to a CSV file where you can then manually review and filter out, and you can actually then update a model from that same exact CSV in that right format, and then it will bring in those filtered out changes into your updated model. But we're not able to do that in this case. So I'm going to show an alternative approach. Because I like using SQL queries. So what I'm going to do is I'm going to just actually edit, copy these objects, and I'm going to select this network, and I'm going to paste in the objects. And so what I did was I just dumped this network into here, right on top of it, and then I'm going to let a custom SQL query sort out the issues. So I have a query here called merge changes, and what it does, it's going to take just a little bit of time to run, but what it does is it's going to loop through each of my different objects, and you can see it found the exact changes that were different between my model and that model. And then whenever it found a difference, it updates my existing model and with the appropriate flag. So in this case, I told it to use an inferred flag just so it stands out for this presentation. So we updated that sewer shed to 3. We updated this pipe to a larger diameter. This one has a larger sewer shed basin. This one has a larger diameter. So it found those and it flagged them, and it also selected them for me. And as it iterates through, it also then kind of deletes out the temporary objects that it brought over from this network. And so that's one approach that you can do this. There's other means, of course. So now if I want to check this model, make sure that it's working, I can click validate. And I'm going to go ahead and minimize or get rid of that. And you'll notice it found a couple problems for me. So that is because my script did not fix this one issue, in that this new pipe was going to a former node that got deleted, and so it needs to be reattached to the correct node. That's pretty easy. I'm just going to edit object geometry and snap it back onto that proper node. So that's done. And then it's also missing the invert elevations because it didn't like how EPA Swim left those blank. So with this pipe selected, I just drag on my elevation inference, click OK, and now that pipe is done. So I can say validate. Oh, actually, before I do that, one other thing. This pipe had a default length, or a length of 400 in EPA Swim. I'm just going to give it the default flag, system default in ICM, which is an indicator to ICM to just simply use the actual length of the shape on the map in map units. So this pipe, based on the shape, happens to be 766 feet. So with that, I'm going to click validate again, and now I get 0 errors and warnings. And so now my model is updated from SWM, and I can once again save the model. So finally, so we talked about scenario management, updating from GIS, data flags, version control, round tripping the data to and from EPA Swim. So finally, we're going to run the model and review some results. So down over here, I have a run library. So I can click update to latest. I can give my run a name, and now I can check any different scenarios that I want to run. And I can also run each of these scenarios with multiple different rainfall events. So I can have a library of different rain data. Let's go ahead and use Greenville 2, which is just double the rainfall. And there's a few other options you can dig into, such as the surcharging method and so on. But one of the nice things about running in ICM is that you can push simulations out to other servers. So if I wanted to run, this is 2 rainfall events times, I don't know, 7 different scenarios. So that'd be 14 different runs. If I wanted, I could run that all on my laptop. It would queue them up in series or in parallel, depending on how I set it up, or a mix. Instead, I'm going to push it out to a separate server because I can. And so So now we can take a look at the job control window and see what's happening. So it created several different run tasks, and it is pushing them to a server that happens to be based in Denver. So because I'm in Chicago and it's not very close, there is a little bit of a lag time, uploading the model and downloading the results to and from that server in Denver. But all in all, it's pretty quick. It might actually run faster if I just ran it on my laptop, but just for fun, just wanted to illustrate that. And so while that's finishing up, let's just jump to a result view in SWM. So one of the things I like about reviewing results in the InfoWorks ICM platform is that it synchronizes everything for you. So you can have dynamic themes like so, where we are theming based on the surcharge D over D. We're theming with the available manhole freeboard. And I can drag this point anywhere on a time series, anywhere that I graph. If I wanted to create a new graph, I can just graph this pipe right here. Let's graph the flow there. So we can graph it, and it synchronizes everything. So as I drag this to different points in time, my map changes according to that time step. My profiles change. The profile applies the map theme in this plan view of the profile. So where there is a freeboard or a flood risk alert on the map, it also shows up in my profile. And it's all pretty integrated and synchronized. And so I can click play, and it animates pretty well. And so there's obviously a lot to data review that I won't really go into, as it's not the core focus of this run. But that's kind of the full round trip of using a SWM model in ICM.